Okay, in this video we're going to be looking at things that are related to counting. Now we're going to be looking at 5 different rules that are related to counting, mainly with permutations and with combinations. So those are the 2 things we'll look at. Okay, now let's define what a permutation is. Okay, now a permutation is this. It's defined as an arrangement of items in which different sequences of the same items are counted separately. Now, to put this into perspective, the order is of importance. Okay? So if we're going to be arranging items in a specified order, and if it's of importance, then that means we do have a permutation type problem. Okay, now next is a combination problem. Now the difference with a combination is this. It is an arrangement in which different sequences of the same items are not counted separately. They're not counted separately. In other words, to put it in perspective, order is not of importance. Okay? So that's the difference between a combination type problem and a permutation type problem. In permutations, the order is important, but with combinations, order is not going to be of importance. Okay? Alright, the next thing we'll talk about is some of the notation that is used in permutations and combinations. So let me give you the notation here. Alright, the notation. Now, the factorial symbol is going to be this. It's going to look like an exclamation mark because that's what it is. The factorial symbol in this case in mathematics is the exclamation mark. What this denotes is this. It is the product of decreasing positive whole numbers. Okay. For example, if I have 4 with the exclamation mark, that represents 4 factorial. And that represents the product of decreasing positive whole numbers. In other words, 4 factorial means this: 4 times 3 times 2 times 1. It starts with a 4 and then it decreases by 1 each time as a product. So if I multiply 4 times 3, that'd be 12 times 2, which will be 12 times 1, which will give me 12. So 4 factorial will be 12. Okay. Because you'll be seeing that in all of your counting rules, in many of your counting rules that are related to permutations and combinations. Okay. Now let's go ahead and look at the 5 counting rules that are discussed in this particular section. And then we'll look at examples of each of these. Okay, so here we have 5 counting rules. And one of them is the fundamental counting rule. And that fundamental counting rule is just simply m times n. Okay? And what this represents is just the number of ways that 2 events can occur. Number of ways that 2 events can occur. And you have to be given the fact that the first event occurs m ways and the second occurs n ways. Okay. So that's the definition of the fundamental counting rule, which is usually m times n. Okay. And one example of that would be this. If you have a 2-character code that consists of a letter followed by a digit, then the number of different possible codes will be 26 times 10. 26 because there are 26 letters in the alphabet, and there are 10 digits in our number system. 26 times 10, that would give you 260 different possible codes. Okay. The second rule is the factorial rule, which I got through talking about, introducing factorial. So the factorial rule is this: your n factorial. And this represents a number of different permutations. Okay. The number of different permutations. Of n different items when all of the n items are selected. Okay. And one example, I can put this on the video, would be this. Let's say we have the number of ways that 5 letters A, B, C, D, and E are arranged. Okay? And all of them are going to be selected, so that means we have 5 factorial, which is a product of decreasing positive whole numbers, so that would be 5 times 4 times 3 times 2 times 1. Multiply that out, you'll get 120. So in this case, there are 120 different ways that the 5 letters can be arranged. Okay, that's the factorial rule. Okay, the third rule is your permutations rule. And there are a couple of permutations rules that you need to know. And this permutations rule is this. This is where or when all the items are different. Okay, and in this case, you have all the items and you're choosing a certain number of items. Okay, and it's this formula, NPR. And what that means is this. You have N items. R is going to be the number of items that you're going to be choosing at a time, at one time, without replacement. Okay, that's what this means. Okay, you have N items that are available, but only R of those items, which is your R, they're going to be chosen or selected without replacement. And that formula is going to be this. N factorial divided by the difference of N and R factorial. So in this case here, an example of that, and I'll do one just like this. Let's say we have 5 letters, A, B, C, D, and E, and they are available. 3 are selected without replacement. Okay, that's very important. So here 3 will be selected without replacement. And we want the number of different permutations in this case. So what we'll do here is the N is going to be 5 because there are 5 items available. 3 are chosen, so it'll be 5P3. And then we substitute our N with the 5, so it'll be 5 factorial divided by N minus R, which is 5 minus 3 factorial. Now, if I simplify this, 5 factorial would be the numerator. 5 minus 3 would be 2 factorial. Now, if I simplify this, I'm going to expand 5 factorial as 5 times 4 times 3 times 2 factorial. And I'm stopping at 2 factorial because if you notice, in the denominator, I have 2 factorial. And with that, I can divide out the 2 factorials. So all I have to do there is just multiply 5 times 4, which is 20. 20 times 3 will be 60. Okay. So the number of different permutations here will be 60. And that's for 5 available items, and I'm choosing 3 at a time without replacement. Okay. So that's an example of the permutations rule, when all the items are different. Alright, number 4 is where some of the items are identical to others. So number 4 is your permutations rule. And this is when some of the items are identical. Okay. Now the way we do that is this. We have n factorial in the numerator. Now the denominator is going to be n1 factorial times that's n1 factorial times n2 factorial, and so on, all the way to n sub k factorial. And I need to explain what those means. Your N1 means this, the numbers that are alike. N2 are the number of items that are alike, and so on, to N sub k that are alike. Okay, now here's an example. Let's say we had 10 letters of the alphabet. And here we got 4 A's, 2 B's, 2 C's, a D, and an E. And here, those items are available, those letters are available. All 10 are to be selected without replacement. So here, all 10 are selected without replacement. Now in this case here, we will use that permutations rule where you have some of the items are identical to each other. So in this case here, your numerator would be the n, which is your 10 factorial because there are 10 items. Now, there are 4 A's in this set of 10 letters. So you can have 4 factorial, then times, there are 2 B's, that's going to be 2 factorial, and then you got 2 C's. That's another 2 factorial. Okay? That's how we set up that particular problem. Now, we don't do anything with a D and the E because there's only one D, so that's like 1 factorial, which is 1. And E, again, 1 factorial, that's also going to be 1. Okay, so now, let's simplify this a bit. 10 factorial will be 10 times 9 times 8 times 7 times 6 times 5 times, and I'll stop at 4 factorial because the denominator has 4 factorial in it. So I'll bring down the 4 factorial and rewrite 2 factorial as 2 times 1 and the other 2 factorial as, again, 2 times 1. So in this case here, the 4 factorials divide out, and also a 2 times 1, that's 2, that can go into 6 3 times. 2 times 1, that's also 2, that can go into this 8 4 times. So I have 10 times 9 times 4 times 7 times 3 times 5, which will end up being 37,800. Okay, so in this case here, the number of different permutations when you have some of the items that are identical would be 37,800. Okay, now later on in this video, we are going to be looking at some examples that are just related to this permutations rule number 4, when some of the items are identical. And then the last one is the combinations rule. This is number 5. Okay, now the combinations rule is this. You have n items and you're choosing r at a time. And here the order does not matter. So here that formula will be n factorial divided by n minus r factorial multiplied by r factorial. Okay. So in this example here, let's say we had 5 letters. Here A, B, C, D, and E. They're available, but we're going to choose 3 without replacement. And the order does not matter, so we can use this combinations formula. So n is going to be 5, so it'll be 5C3. And that's going to be equal to n factorial. N is 5, so it'll be 5 factorial divided by n minus r. That's 5 minus 3 factorial times 3 factorial. And now if I simplify this, this will be 5 factorial divided by 5 minus 3 will be 2, so it'll be 2 factorial times 3 factorial in the denominator. I'll expand 5 factorial as 5 times 4 times 3 factorial. And 2 factorial will be 2 times 1. And I'll leave the 3 factorial as is in the denominator because I can divide out the 3 factorials in the numerator and the denominator. So in this case here, 5 times 4, that's 20. 2 times 1, that's 2. 20 divided by 2 will be 10. So, since order does not matter, the number of different combinations is going to be 10. And that's for 5 letters, and I'm choosing 3 at a time without permission, without replacement. So these are the 5 rules that you'll be using in this particular section. So here, let's go over some examples of these particular rules. Let's start with this first example here. A thief steals an ATM card and must randomly guess the correct 3-digit PIN code from a 6-key keypad. Repetition of digits is allowed. What is the probability of a correct guess on the first try? Okay, so here there's a there's the keypad with 6 digits on it, and repetitions are allowed. So on the first number, he gets to choose 6. The second number, he gets to choose 6. The third number, he gets to choose 6. This is a 3-digit PIN code. Okay? So if I multiply 6 times 6 times 6, I'm going to get 216. Now, the probability of getting a correct guess on the first try, that's just simply going to be 1 over 216. Because there's only one correct 3-digit PIN code on that ATM card. And for him to get it on the first try, that probability will be 1 out of 216. Okay. Alright, now example E2. A fan of country music plans to make a custom CD with 14 of her 26 favorite songs. How many different combinations of 14 songs are possible, and is it practical to make a different CD for each possible combination? Okay, it is a combinations problem, so that means that order is not of importance here. So we use the combination rule, which means we're taking 26 of our favorite songs and we're choosing 14 without any importance of the order. Okay? So now, that's where we use this combinations rule that we talked about here. NCR is equal to n factorial divided by n minus r factorial times r factorial. So the numerator will be your 26 factorial. In the denominator, 26 minus 14 factorial divided by, times r, which is 14 factorial. Okay. Now in this case here, the numerator is your 26 factorial. 26 minus 14 is going to be 12, so that's 12 factorial times 14 factorial. Now in this case here, we need to expand 26 factorial, and this is going to take a while because you got 26 times 27 times 28 times 29. Correction. It's decreasing. So in this case here, 26, and then you got 25 and then 24, and then 23, and then it's decreasing. So this is 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19 times 18 times 17 times 16 times 15 times 14, and I'm stopping at 14 factorial because if you notice, in the denominator I have 14 factorial. Okay, but I do need to expand 12 factorial as 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then bring over the 14 factorial. Because in this case here, I can divide out the 14 factorials in the numerator and in the denominator. Okay, but I can do some cross dividing with some of the numbers in the numerator and the denominator. Like, for example, I know with 24, that's 12 times this 2. So if I take the 12 and the 2, I can divide that out with the 24. And I know with 11, that goes into 22 2 times. With the 10, that 10 goes into 20 2 times. And I also know that 9 goes into this 18 2 times. Let's see, with the 8, well, with these 2's that I got up here, 2 times 2 times 2, that's 8. All that can be divided out with this 8. And I know this 7, well, 7 times this 3 would give me 21. I can divide that out with that 21 up here. And let's see, 6, well, this 4 goes into this 16 4 times. And I know 6 times 5 will give me 30. But let's do this. 5 goes into this 15 3 times. And this 6 can go into something. Now, 4 times 3, that would give me 12. But if I divide that out, that's going to be a 2 up here. That divides out with that 6, because 6 can go into 12 2 times. So all the numbers in the denominator are gone. So I'm left with 26 times 25 times 23 times 19 times 17 times the 2 up here. Now, my final answer there will be 9,657,700. So there are 9,657,700 different CDs of 14 songs that can be made. Now, would it be practical to make a different CD for each possible combination? Unfortunately, that answer would be no. Okay. Now, you can do this on the calculator, so let me show you how this is going to be done. Okay. I have 26C14. I have to enter the number first. That's 26. And then I'm going to press the button that says Math to get this menu. Now, we're dealing with probability, so I want to use my right arrow key to highlight the probability menu. Okay. Now, if you look under number 3, you're going to see something that says NCR. That's your combinations rule. So you can arrow down to NCR and press enter. And then you're going to enter the number to the right of the C, which is, in this case, 14. And then hit enter. And you'll see I came up with exactly the same number when I used that particular rule. So you have 9,657,700. Okay? So that's how we can use the calculator to apply the combinations rule. Okay, let's look at the next example. A presidential candidate plans to begin her campaign by visiting the capitals in 3 of 41 states. What is the probability that she selects the route of 3 specific capitals? Is it practical to list all the different possible routes in order to select the one that is best? Now, in this case here, she's dealing with order. Order is going to be of importance, so instead of combinations, we're going to be using permutation. And we're dealing with 41 states. She's choosing 3. And I'm going to show you how to use the permutations rule here. Okay, so that permutations rule that we just got through talking about is this one. NPR is equal to n factorial divided by n minus r factorial. So in this case here, your n is 41, so that would be 41 factorial divided by 41 minus 3. N is 41 and r is 3. So it'll be 41 minus 3, and that quantity is going to be factorial. Let's simplify this. This is 41 factorial divided by 41 minus 3 will be 38, so that'll be 38 factorial. Now, if you were to expand 41 factorial, you have 41 times 40 times 39 times 38 factorial. And I'll stop at 38 factorial because if you notice, in the denominator, I have 38 factorial. So if I divide out your 38 factorials, I just have 41 times 40 times 39, which will be 63,960. So in this case here, there are 63,961 ways that this presidential candidate can select a route of 3 specific capitals. Now for the probability, of selecting the route, there's only one way to do that, so it'll be 1 over 63,960. So the probability of selecting a route of 3 specific capitals would be 1 over 63,960. Now, is it practical to list all the different possible routes in order to select the one that is best? No, it isn't. Because that's 63,960 is a large number, just like the one in the second example that I did in this video. Okay. All right, example E4. A classic counting problem is to determine the number of different ways that the letters of magically can be arranged. Find the number. So we're dealing with the word magically. I'll rewrite that. Now notice in this word magically, you got 2 A's and 2 L's. So we're going to have to use the permutations rule when you have some of the items that are identical. And that's this rule number 4. N factorial divided by n1 factorial times n2 factorial all the way to n sub k factorial. Okay? So in this case here, the n factorial is the number of items, number of letters in the word magically. There are 9 letters in the word magically, so we have 9 factorial in the numerator. The denominator are going to be the factorials where the letters repeat. In this case, there are 2 A's in magically, so that's 2 factorial. Also, there are 2 L's in magically. That's another 2 factorial. Okay. M and the G and the I and the Y occur only one time. Also, the C occurs one time. So let's simplify this. 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 factorial. The reason why I'm stopping at 2 factorial because I have a 2 factorial in the denominator. And I'm also going to expand the other 2 factorial as 2 times 1. So as you'll see, in this particular situation, one of your 2 factorials is gone. And 2 times 1, that's 2, that can go into this 4 2 times. So I have 9 times 8 times 7 times 6 times 5 times 2 times 3, which will be 90,720. Okay. So there are 90,720 different ways that the letters magically can be arranged. Another example similar to that would be this: how many different ways can the letters of notebook be arranged? How many different ways can the letters of notebook be arranged? If you notice, there are 3 O's in the word notebook. So we also have to use that permutations rule when you have some of the items identical. There are 8 total letters in the word notebook, so we use 8 factorial in our numerator. The denominator, only 3 O's in this word notebook, so we use 3 factorial. And that's all there is to it, because the N and the T, the B, the K, and the E occur only one time. Now if we simplify this, this will be 8 times 7 times 6 times 5 times 4 times 3 factorial. And that's also divided by 3 factorial as well. And in this case here, we can divide out the 3 factorials. So you have 8 times 7 times 6 times 5 times 4, which will be 6,720. Okay. All right. Example E6. Find the probability of winning a lottery with the following rule. You select 6 winning numbers from 1 to 30 in any order, no repeats. As you can see here, order is not of importance, so that means we do have a combination type problem. So here, we know we're going to have a combination problem. There are 30 numbers, 1 to 30. We'll select 6 of them. So it'll be 30C6. And in this case, that's where we use that formula where n factorial, that's 30 factorial, divided by n minus r, that's 30 minus 6 factorial, times 6 factorial. So here we got 30 factorial. 30 minus 6 is 24, so that's 24 factorial times 6 factorial. Now the 30 factorial can be expanded as 30 times 29 times 28 times 27 times 26 times 25 times 24 factorial. Because notice you got 24 factorial in the denominator. Now that 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. And in this case, your 24 factorials divide out. And let's see. If I do 6 times 5, that's 30. I can divide that product with that 30 factorial. And let's say 4 goes into 28 7 times. Three goes into 27 9 times. And 1 times 2, that's 2. That goes into this 26 13 times. Okay. So in the numerator, I got 29. Now I'll write out what I have. 29 times 7 times 9 times 13 times 25. and that'll end up being 593,775 if you were to multiply all that out. So we know that there are 593,775 ways of selecting 6 numbers from 1 to 30 in any order without any repetition. Now we want the probability of winning the lottery, and there's only one way of winning the lottery, so the probability of winning would just be 1 over that number, 593,775, and we'll just leave it as a fraction. Okay. All right, another example would be this. In designing an experiment involving a treatment applied to 7 test subjects, researchers plan to use a simple random sample of 7 subjects selected from a pool of 41 available subjects. Recall that with a simple random sample, all samples of the same size have the same chance of being selected. Okay, that's the definition of a simple random sample. All samples of the same size have the same chance of being selected. And in part A, we want to find out how many different simple random samples are possible. Now here, the order is not going to be of importance, so we have to use the combinations rule. We have 41, and we're choosing 7. Okay. Now, instead of using that particular rule that I just showed you with the combinations rule, I'm going to go ahead and use the calculator. For 41C7, we enter the 41, then hit the math key, hit your right arrow key to PRB, and then you're going to select number 3, which is NCR, and then type in the number after the C, which is 7. So you have 41 NCR, then 7. Then hit enter, and that will be, that will be 22,481,940. So that means that there are 22,481,940 ways of selecting, simple random samples. 22,481,941 simple random samples are possible. Part B is this. What is the probability of each simple random sample in this case? Well, the probability, each one has an opportunity of being selected, so for each simple random sample, its probability is simply going to be 1 over 22,481,940. Okay. Now you could use that combinations rule if you want to and see that'll end up being 22,481,940. Okay. And then the last example, when testing for current in a cable with 11 color-coded wires, the author used a meter to test 4 wires at a time. How many different tests are required for every possible pairing of 4 wires? Okay. So the order is not important here, so this will be 11C4. Okay. You can use the combinations rule that's given, or use the calculator. So here, we type in the 11, then press the math key, and then go to PRB using your right arrow button, and then select number 3, which is in CR, and then type in the number 4, which is after the C, and then hit enter. That's going to give you 330. So in this case here, there are 330 different tests that are required for every possible pairing of 4 wires. Okay. Okay, now I do need to go back to one of the permutation problems that I did earlier. And that's this one with the presidential candidate. Instead of using that formula, you can also use that permutation command that's on the calculator. So with that 41P3, you'll type in 41, go to math, press the math key, hit your right arrow key to PRB. You should see under number 2 NPR. So you'll select number 2 for NPR because it's a permutation problem, and then type in the number that's after the P, which is your 3, and then hit enter. And you'll see that I came up with that 63,960 that I came up with in that particular problem. Okay. And also, one more thing, since I was dealing with factorials here, by definition, anytime you have 0 factorial, that's automatically equal to 1. And that's just by special definition. Okay. So anytime you have 0 factorial, that's always going to be equal to 1 by just a special definition. There's no proof that I can come up with you to show that 0 factorial is going to be 1. It's just by definition. Okay, so this will conclude this particular video on counting.